Good evening to anyone from Australia, and also good morning and good afternoon. So alumni who are joining us, and also our students and other guests who are joining us for this webinar session. I will start the introduction so that in the interest of time, and then we will go on to the actual session for tonight. Before I go ahead, I'd like to acknowledge the traditional owners of the land and pay respects to the elders past and present. And if there are any Indigenous or Aboriginal members in the audience, I'd like to acknowledge and welcome you as well. For those who haven't been to this webinar series, so my name is Udeshka Wijewardena. I'm the Alumni Engagement Manager for the Faculty of Science. And I just take you through a little bit of the format of tonight's session. There will be a couple of minutes of introduction to the School of Earth, Atmosphere and Environment, from which our presenters are from, followed by a 30-minute presentation from Professor Andrew Mackintosh, who's the head of School of Earth, Atmosphere and Environment, and a 20 minutes of Q&A session, which gives you an opportunity to ask any questions. Throughout the presentation, if there are any questions, I will request for you to put them in the Q&A section just below the screen, and they will be answered during the session. So today I'm actually joined by Professor Andrew Mackintosh. Say, there's Andrew, and then Professor Andy Tompkins, who is going to be the moderator for tonight's session. So Andy, I will be introducing a moderator first, and then I'll hand over the session to you. So Andy is actually a professor of Earth and Planetary Sciences, and he's also the deputy head of school for the School of Earth, Atmosphere and Environment. Andy's research focuses in the field of economic geology and understanding how, when, and where critical mineral ore deposits form. He's published recently on new ore deposit models, which are relied on by exploration geologists to find new resources currently. And Andy has received several prestigious fellowships over his career, including Albert Ingenuity Fellowship, a Monash Fellowship, and also ARC Future Fellowship. He's also a winner of some international awards with the Society of Economic Geologists, in particular the Waldemar Lindgren Award in 2008 and the SEG Silver Medal in 2021. And he's also a Lindgren Fellow of the Society of Economic Geologists. He has also recently completed a stint as the Associate Editor for the journal Economic Geology. So I'd like to leave you now and hand over the session to Professor Andy Tompkins. So Andy, I'll leave the session with you now.
Okay, thanks, Edie. Thanks very much for that. So, hi everybody. First, I'm going to give you a bit of an overview of what our school is like. So, our school is one of the top Earth science, Earth atmosphere and environments schools in the world. Actually, so we're ranked top 50 in the world for geology, top 50 for geophysics, and we've got some really outstanding world-leading research centres as well. So. We've got a Centre of Excellence in Weather of the 21st Century that was just awarded recently. And Andrew here, who's presenting tonight, is one of the directors of an ARC Special Research Initiative Centre. It's called SAFE, which stands for Securing Antarctica's Environmental Future. And both of those two big research centres have on the order of $35 million each. So they're quite big research things that are happening in our school. So all of that is kind of underpinned by about 700 odd undergrad students. There's about 100 PhD students here, and we've got about 50 staff, many of which are postdocs, and about 30 plus of which are academic staff. So we're a pretty big school. Some of the latest stuff we're doing is developing sort of new research directions in critical mineral resources, that sort of thing. So that's who we are. I'm going to introduce Andrew now. So Andrew is, as Udi said, Andrew is our head of school. and he's been working on glaciology for a long time. So his research aims to improve our understanding of glacier and ice sheet response to climate change, including assessing the impacts on sea level, water resources, and ecosystems. And he's a regular commentator in the media and has been lead author on of the IPCC special report on the oceans and cryosphere in changing climate, which was published in 2019. His work has taken him to many places around the world. I'm quite jealous of where he gets to go to. So he's been to Antarctica quite a few times, and Greenland. I'm quite jealous of the type of work he gets to do. You'll see some of it today. Prior to coming to Monash in 2019, he was director of the Antarctic Research Centre, as well as professor of Earth and Climate Sciences within the School of Geography, Environment and Earth Sciences at Victoria University of Wellington in New Zealand. He received the New Zealand Prime Minister's Science Prize in 2019, which is a bit of a big deal. And he has his PhD from University of Edinburgh over in Scotland, postdoc from Utrecht University, and he's held visiting positions at Columbia University and the University of Bristol. All right, there we go. That's Andrew. And I'm going to hand it over to him now and let him put on a bit of a show for you. Take it away, Andrew.
Thank you so much, Andy. Can you see and hear me okay, including the screen?
Yep.
Yes, we can.
All right, thank you so much. Australia is the only continent on Earth that doesn't have any glaciers. And so some of you might be wondering why I'm talking about glaciers tonight. Glaciers, as they melt, impact the whole world, and I'll try to convince you that they're important and things that we should care about. I also do a lot of work on the Antarctic ice sheet. I'm mostly going to talk about mountain glaciers today, and there's another story about the ice sheet that I could tell in the future. I'm going to get stuck straight into it because I think there's a danger that I might run too long, so let's go. Back when I worked in New Zealand, we set up time-lapse cameras of glaciers. This one is Franz Josef Glacier in the Southern Alps, and you can see it here flowing downhill. You know, through the repeat photography, you can see the flow of ice. And there's a fascinating Maori story about Franz Josef Glacier. The Maori name for this glacier is Kara Roimaita or Hina Hukatere, the tears of Hina Hukatere. And the story, I'll play this again because it's so interesting to look at. The story is that Hina, a young Maori woman, was trying to convince her partner Tawe to climb in the mountains. He didn't like it. He was scared of the mountains. Eventually, he relented, and they went for a walk. And he slipped and fell to his death. And then Hina cried, and her tears froze and became the glacier. You can see at the end of this video here, the glacier sort of parting and peeling around bedrock. And we made this video back in 2014. And now well, it's a year ago now, but in March 2023, you can see the ice has receded all the way back up to that area of bedrock. So the retreat of glaciers in New Zealand is something we see, unfortunately, all over the world. Here you can see the Rhona Glacier in the European Alps in 1900, and then in 2008, the glacier has now retreated even further over the bedrock lip, where you can see that black arrow. It's further up the hill. It's still there, but disappearing fast. So, you know, why are glaciers behaving like this? What can we expect in the future? What will be the impacts on mountains, but also more broadly worldwide? These are some of the questions that I try to answer in my research. And we carry out this research using a combination of observations and models, so computer models. This is a particular numerical computer simulation of glaciers in the central part of the Southern Alps of New Zealand. And I'll just show you a couple of images that will sort of give you a feeling for how glaciers are changing everywhere, not just in New Zealand. And maybe some of you have been here. This is a place often visited by tourists. Towards the bottom of the image is Mount Cook Village on the eastern side of the Southern Alps, and then on the far side is Fox Glacier and Franz Josef Glacier. I just showed you that time lapse of Franz Josef. Right? So this is a simulation of something that looks quite close to the present day ice extent in that part of New Zealand. And under RCP 8.5, and I'll explain what this is in a minute, by 2100, so this is the end of this century, most of the ice is gone in this computer simulation. Now, RCP 8.5 is a climate change scenario where there's no real attempt to mitigate the effects of global warming. Emissions continue to increase through the 21st century, and there's about 4 degrees of warming here in New Zealand as a consequence of that climate change scenario. And it's hard not to get a bit depressed as a glaciologist, right? You look at these sort of simulations and get quite concerned about what the future might look like. But there's a very clear difference between this kind of scenario where we just sort of burn all our available fossil fuel resources, and one where we keep our climate closer to the Paris Agreement that results in about 2 degrees of global warming. And in such a scenario, the ice still retreats, but not nearly as much. And by the end of the century, this again is a simulation for 2100, in this part of New Zealand, we would still have glaciers. Our children and our children's children would be able to go and visit glaciers and recognize them, and they would still be features in the landscape. Smaller than today, but still there. Under the warming scenario, much warmer conditions, really the only ice that's left is on the very highest peaks, or in some places in the valleys where it's covered in debris and it's essentially not a glacier anymore. This kind of scenario that I just described, it plays out worldwide. So I'm now showing another video. This is not my work this time, it's from a colleague, looking at the retreat of the Monash Glacier in Switzerland. And you can see we're getting up to the present day now. And then again, towards the middle of this century, and then further towards the end of the century, most of the ice is gone in this kind of scenario. And no matter where we do this kind of work worldwide, and in fact, worldwide glacier modeling studies like this all show similar kind of effects. And today, the image to the right shows, with the big circles, shows where all the glaciers are located on Earth. And the size of the circle represents the amount of ice that's present. So most of the ice is in Antarctica, as you know, but there's considerable glacier ice in places like Arctic Canada, in Alaska, in southern South America. And if all of that ice was to melt worldwide, it would cause about 0.5 meter of sea level rise. And the current scenarios for glaciers indicate that about up to half of that ice might be lost by the end of the century worldwide. So, that's a lot of ice missing. And it's, if I give you a number like that, half might be lost. It's perhaps not that easy to think about what that actually looks like, but let's go here. This is a map showing computer simulations of all glaciers worldwide. And the thing to look for here are the black circles with the empty space inside. They're essentially extinct glaciers at the end of the century. So you can see under this particular simulation, which is what happens to worldwide glaciers in response of 2 degrees of warming. So again, this is like the Paris Agreement. This is the good scenario in a way. We still lose considerable glacier ice from around the world. In places like Europe, you lose a lot of ice. The continental United States loses almost all of its glaciers. And the places where there's considerable, extensive and thick ice today retain some ice, but a lot of it's gone. So the green and orange and red colors indicate sort of, half to 80% of the ice is missing by the end of the century in those locations. So it's not a good news story for glaciers, but the choices we make in terms of emissions will make a big difference to the outcome. And why does that matter? Well, particularly in Central Asia, where we have the majority of the world's population, the world's 2 most populous countries, India and China, billions of people rely on the meltwater from glaciers, but also from snowmelt to recharge their rivers. So you can see this map shows major river basins, and the light blue color represents areas where snow and ice melt is really critical to the river flows. And there's this headline here: snow and ice loss will affect at least 60 million people in Asia alone. I mean, that's just the direct areas where the ice is being lost, and actually the broader impacts are much greater. So, billions of people, some of the major economies on Earth, strongly impacted by climate change and the effect on river flows. I've shown a couple of stars here. You can see one in the Yangtze Basin and another one in the Indus. And I just want to show you what these environments actually look like. I was actually just in the Yangtze Basin about 2 weeks ago, actually, on the eastern edge of the Tibetan Plateau. And you can see this is a like vibrant ecosystem full of lush vegetation and lots of rain. There's actually a glacier down through the mist in the central image that you can't really see particularly well. But this is a rainfall-driven environment where if all the ice was to melt away, it's very unlikely it will be less of an issue than in a place like this next slide. So now we're over in the Indus Basin, the major river of Pakistan. This particular glacier is in India, but the headwaters are in India and it flows into Pakistan and it becomes the major water resource there. And you can see it in Ladakh, there's almost no vegetation. There's hardly any rainfall, and the civilization, all at the scale from small villages all the way to big cities is absolutely reliant on the meltwater from glaciers to live. So exactly where you are in a mountain range makes a big difference to what the future might look like. And this is another picture of mine from the upper Indus Basin. You can just see there's no vegetation whatsoever. This is an incredibly dry environment. We're up on the Tibetan Plateau in the rain shadow of the Himalayas to the south. So back when I was a IPCC lead author in 2019, I helped with this diagram, which represents what's going to happen to the world's rivers that are being fed by glaciers. And I'm just going to, you can look at it yourself and see if you can work it out. But there are just a few kind of headlines here. One is that as glaciers melt, we actually expect to get more water initially. Like as we get lots of melt, then it creates a lot of water. That's not too surprising. A lot of that water will flow down the rivers during the summer. And actually in some places where we're experiencing drought, you'll get a flux of water during the summer that will help to alleviate drought. So that's sort of a good news part about melting glaciers, that in some places melting will buffer drought. But as glaciers dwindle and disappear ultimately, that source of water is no longer present. And there's this idea that where we reach the peak of water flow, it's called peak water, and peak water will actually differ in all parts of the world depending on how thick the ice is and how quickly it's melting away. So you might just ask yourself the question, like, do you think we're at peak water yet? Which areas might be at peak water? What do you think? Well, here's a simulation of peak water and when we think we'll get there. And you can see that it's a little sad, but we've already passed peak water in the European Alps. But in some of those river basins I was talking about in India and Pakistan and China and so on, peak water is still some distance into the future. Right, so managing the water flows from these basins is really dependent on how much ice is there and what's going to happen, and we can predict that and help to manage the outcomes as a consequence. This is really important for things like development of the economies of these nations. The impacts on Australia are also important because if there's destabilization of these economies, of course, it has this broader impact on us. When I started studying glaciers, we often saw glaciers that were relatively close to equilibrium. They were covered in the snow during the winter. The snow largely melted away in the summer in the lower part, but it remained in the upper part. But in the last few decades, we've increasingly seen all the snow disappearing. And I'm really quite concerned about this because it creates a feedback where even more melt occurs. And just to show you a little video taken from helicopter flying over a glacier in New Zealand. And this is during March 2023. And you can see that there's really no snow to be seen, no residual snow at the end of summer. And this is an example of what we're calling extreme melt, just not the usual melt of glaciers. And this is an aerial photograph of a very small glacier in New Zealand that in this case, it's mostly covered in snow. This is what we would expect to see for a happy glacier, one that's in equilibrium, that's relatively stable. But increasingly, we're seeing the entire snow cover sort of completely ripped off these glaciers. And we're left with an exposed ice surface that becomes darker and then melts more as a consequence. And this is a real worry, right? A few years ago, we tried to get to the bottom of this to answer the question, why is this occurring? Could this occur in a climate that hasn't been influenced by humans? Is it actually a direct result of anthropogenic global warming? These are important questions to try to answer. And my PhD student, Lauren Bargo, went about trying to answer this question using a computer modeling approach. And these are some of her results. It takes a minute just to walk through these. These two charts are for two different glaciers, Brewster, which I just showed you, and Rolleston's the little glacier we just looked at as well. And mass balance on the x-axis is basically an indication of the health of the glacier. So if it's 0, then the glacier is in equilibrium. If it's 1, 2, or 3, then ultimately a glacier would grow with positive mass balance. But if it's in the negatives, then we're seeing something a little bit unusual. And each of the curves represents a probability distribution for the mass balance of a particular glacier. And the black probability distribution is what we would expect in a climate that hasn't been influenced by humans. And the red curve represents the climate that's been anthropogenically influenced. And then the black dotted lines actually show the measurements from particular glaciers. So not just a model, but data. And what you can see here is that these 2 years, 2018 and 2011, both at Brewster and Rolleston glaciers, sit outside the probability distribution, even of the anthropogenically influenced climate, and shouldn't really be happening. We're seeing melt that's beyond the extreme of what we would expect, even in a climate that's influenced by humans. And maybe you're a bit skeptical about computer models and their value. So I thought I'd just show some actual data as well. In Switzerland, people have been measuring the state of glaciers for more than a century. There's an incredible record of glacier observations. So these are not models. And in the top right, you can see all these bar graphs that indicate negative balance. That means that every single year in Switzerland, glaciers are melting. There's no gain of ice at all. And some years are much bigger than others. So in 2022, you can see a huge amount of ice loss in that figure at the top. And the figure at the left is basically similar to my model simulations that I was just showing you, except it's rather than models, it's data. And you can see that the 2022 melt year sits way outside any previously measured melt year on a particular glacier. Right, so we do think there are extremely unusual melt events occurring on glaciers now, and we don't fully understand what the consequences of those will be. And in fact, those model simulations that I showed you earlier for the future of glaciers don't really take into account these extremes, and that's a bit concerning to me. What does extreme melt actually do? So I just showed you that 2011 was a big melt year in New Zealand, and then 3 years later at Fox Glacier, you can see the terminus of the glacier, the hillsides slipping down behind as the glacier retreats. There's a bunch of people walking on the terminus here. Used to be able to just walk onto the glacier and take a tour up the ice. But during this year, in about 6 months, the whole terminus basically collapsed in on itself. And the tourism industry here basically changed forever. The only way of getting on this glacier now is to climb into a helicopter and fly up onto a safe part of the glacier tongue. And that in itself, of course, is helping to create even more global warming. So there's a bit of an irony there, but the impact on tourism from this kind of ice retreat is obviously rather extreme, but there's also an impact here on slope stability, and worldwide as glaciers retreats, we're seeing slopes fall down. We're also seeing glaciers fall down. So in some situations recently, we've seen whole sections of glaciers slide off mountains, which hasn't been observed previously. And we think it's something to do with what's going on underneath the ice as the underside of the glacier warms up and creates meltwater, which is a lubricant and then allows whole sections of an ice body to fall down a mountain. So let's have a look at this one. We're in Kyrgyzstan in Central Asia, and you can see a whole section of a glacier falling off. This video really made the rounds on the internet, and I don't have the rest of it here, but the person who was taking the video actually ended up getting buried in debris, and everyone wondered why they didn't run away and what they were doing filming it. They were actually walking along the top of a ridge and there was nowhere to go. And they walked behind a rock and took shelter behind the rock, and all the sort of snow and ice just settled around them and they were fine. But that's an incredibly spectacular glacier collapse. And yeah, unfortunately, we're seeing more of this kind of thing. So I'm going to move on now to Antarctica. I've just got a few slides about Antarctica, but it's a bit hard to talk about melting glaciers without talking about the largest glacier on Earth, the Antarctic ice sheet. And this is a video that shows how the mass of Antarctica is changing and how it's changed since 2002. And it's a bit of a complex story in some respects, spatially, as you'll see, but the overall signal is very, very clearly one of ice mass loss. So let's have a look. So first of all, in the big map, you can see that the flow of ice, that's what all these little sort of little vectors are. And the red colors here indicate places where the Antarctic ice sheet is losing mass. So particularly in West Antarctica, over here, and on the Antarctic Peninsula. But you can also see some mass loss in East Antarctica. This is really to the south of us here in Australia. This is probably to the south of Melbourne, and over here sort of to the south of Perth. I'm just letting the video stop. So here you can see a complex picture spatially of mass loss, especially in West Antarctica. But there are also areas of mass gain in Antarctica. Up here in Dronning Land in East Antarctica, there's been an increase in snowfall that's resulted in the blue colors, so a gain in mass. And here in the sort of inland parts of West Antarctica, there have been ice dynamic effects that have basically caused like parts of the ice to slow down and then build up. So as glaciologists, it's our job to try to understand these spatial patterns, but also not lose track of the overall signal, which is a sort of major ice loss during this period. Now, over here in West Antarctica, particularly in the Amundsen Sea, which is this section, and at Pine Island Glacier and Thwaites Glacier, we've seen the largest amount of ice loss. I wrote a little paper about this just a few years ago, showing the mechanism that's causing ice retreat in this part of Antarctica. And rather than on mountain glaciers, it's the melting from a warming climate above that's causing the glaciers to retreat. But in Antarctica, it's mostly the warming of the ocean under the ice sheet and over the floating parts of the ice sheet, which are called ice shelves, that's causing the ice to retreat. And that ocean forcing is combined with the dynamic kind of peculiarities of glaciers in Antarctica. So what you might be able to see in these pictures is that there's this sort of cavity underneath the floating ice shelf. And as a glacier goes from one point up here where it's stable to a second point below where it's moved off this sort of stabilizing bedrock high point, it allows more warm water to get underneath. But also, as the ice moves backwards, it thickens and it gets steeper, and that causes it to flow faster and lose even more ice. So what I'm talking about here is called a positive threshold. We have a warming ocean that's causing ice retreat, but as the ice retreats, it takes on its own dynamic behaviors, and that enhances even more and causes even more ice retreat. So understanding what's going to happen to the future of the Antarctic ice sheet requires us to understand the detail of this climate forcing, but also the very complicated dynamic feedbacks, and including the sort of things that can cause snow gains as well, like I showed a minute ago. This is a big job. It's not something that a single scientist can take care of. It requires whole teams to really understand what the future of the ice sheet is going to do. And you might think, well, why is all this important? I've been talking about mountain glaciers and how they're retreating, how they might produce 20 centimeters of sea level rise by the end of the century. And I just talked a bit about the Antarctic ice sheet. The Greenland ice sheet in the Arctic is also retreating rather rapidly. All of this is contributing to sea level rise. And in these two plots you can see here, the top one just shows you how we expect the climate to warm under different assumptions about what's going to happen to greenhouse gases in the future. And the bottom plot shows the associated sea level rise. Now, sea level rise is caused by a combination of factors, including the melt of glaciers, the thermal expansion of the ocean as it gets warmer, and also the melting of ice sheets. And they collectively turn into these different scenarios of what the future might look like. But this is a diagram from the latest IPCC report, the one that followed after the report I was involved in. And what you can see here is that by 2300, so a few hundred years further into the future, we can get very, very large amounts of sea level rise. And not only that, but if you look at the figure to the far right and read the text, you can see sea level rise greater than 15 meters cannot be ruled out with high emissions by 2300. This is because we think that parts of Antarctica might be becoming so unstable that once they retreat, they perpetuate, you know, the retreat, and even more occurs, and it sort of leads to this runaway feedback where a huge amount of ice is lost. And at the moment, the glaciological community can't rule out that this might happen, which would cause huge changes to the world's geography. And in Australia, that would cause, you know, billions of dollars of infrastructure to be put at risk. This quote from Will Steffen's actually really quite out of date now. $226 billion of infrastructure in Australia is at risk to if there's 1.1 metre of sea level rise. But that's 2008 dollars, and it needs to be updated. But right, a huge amount of Australia's most critical infrastructure that's so close to current day sea level. I thought I'd put this up just to show you what the impacts in Melbourne might look like. Melbourne is actually not the world's worst city when it comes to vulnerability to sea level rise. As you might expect, places like you know, the Yarra, where it enters the bay, various other parts around the bay have low relief and are more vulnerable to sea level rise. That's also true for Western Port Bay. But the city is largely built on hills that are, you know, more than a few tens of meters above sea level, and only a few % of our population is at risk of sea level rise, you know, by the end of the century. But the scale that I'm showing you here is exactly the same as the one in the next image. And for a city like Shanghai that's built on a mega delta, you can see this enormous city is completely vulnerable to sea level rise on that scale. Now, it could be that Shanghai, I mean, it's one of the world's biggest economies. Maybe they've got some ways of, you know, building barriers and protecting themselves from sea level rise and adjusting to this. There are many other coastal locations, the Pacific Islands, some of the mega deltas in countries that are less developed that are particularly at risk of sea level rise. So I just wanted to keep in mind those contrasts. You know, some places will get flooded almost completely under those sorts of scenarios. So answering the question about, you know, what's going to happen to the ice sheets in the future, how can we predict future sea level rise, what will the impacts be by the end of the century and beyond, like I said, requires a team. This team up here is one based in the School of Earth, Atmosphere and Environment. All of us are working on trying to understand either the past, present or future of glaciers and ice sheets to better constrain future sea level projections, to better understand mountain hazards and also predict meltwater impacts in the world's major rivers, particularly ones that are feeding the huge economies of Central Asia, for example. And I'm really proud of this group of people that are trying to answer these big questions. And that's the end of my talk today. We are part of a special research initiative that Andy mentioned at the start, Securing Antarctica's Environmental Future. We've got about another 4 years to run, and we'll hopefully answer some of these big questions about what the ice sheets will do in the future. So thank you very much.
All right. Thanks very much, Andrew. That was really interesting. Justin's already asked a question in the Q&A box there. What I might do is use it as a way of asking a slightly different question to get us going on questions. He's basically asking, is Antarctica likely to get explored for minerals and that sort of thing? I might sort of do an initial answer and say that's going to be too late. We can't get the minerals we need to address climate change in that time frame, but by the time the ice is gone in Antarctica. But one one question I had was about, are we locked in to losing Antarctica's ice entirely, or is this reversible?
So
Over a long term, of course.
can I answer the first part just a little as well? But an interesting thing about Antarctica is that it's currently protected by the treaty system, which precludes any kind of exploitation of mineral wealth. And it's a really good example, actually, of a intergovernmental agreement that is working. And I know that a lot of people are cynical about intergovernmental agreements in the current climate, but this one's still holding strong. But Andy, with your question, are we locked into losing sections of the ice sheet? It's actually a really controversial question, and my community haven't reached agreement on this. And I reckon that most of us think that parts of West Antarctica will be very hard to keep in place under current and projected warming. My feeling is the consensus is now that, you know, like we're going to lose a big chunk of West Antarctica. But to what degree that's mitigated by, for example, some growth in East Antarctica and is a little bit hard to say. I think of course, even in the last couple of decades, the trajectory has been one of overwhelming ice loss, and I think that will continue. But predicting the actual impact from Antarctica is pretty challenging.
Yep. So, I mean, I'm interested in that because as a geologist, I tend to think on millions of years of timescale, and over geological time, Australia's Antarctica's, or the position of Antarctica's, had no ice at times. While we're talking, everybody, type your questions into the Q&A box, and we can ask Andrew some more questions. So to me, I've always wondered whether, are we actually locked in at this point already? If we keep, if we take to 2050 to deal with some of these things, how long does it take to get locked in, and that sort of thing, I guess.
Yeah, but we are, but the actual threshold for ice loss in each basin in Antarctica is different. So for each increment of additional warming, we have the potential to lose another system, but it's not all or nothing, right? You kind of lose one at a time. Actually, I mean, you mentioned geological evidence for low ice volumes in Antarctica. Certainly exists, and it's pretty helpful actually for thinking about what the end member states might be under future warming scenarios. So, for example, we see that during the last interglacial, which was like 130,000 years ago, climate was sort of not that different to today, and there was probably about 5 meters of sea level rise relative to today at that time, and that's a lot, actually. It shows you what happens when there's sufficient time for an ice sheet to equilibrate to the current climate. And right now we're in an extremely fast period of change, and the equilibration will take centuries to millennia. So one of the things that worries me is that people talk about short-term projections, but I actually think that the long-term impact is really important, even if we're not around to see it. Like, if it bothers me that what we're doing now could have implications that stretch out over centuries.
Yep. So I guess we're getting a few more questions in the Q&A now. So Marie's got one. I'll ask this one. It's a non-technical question. So this is probably a pretty important question, actually. So she's saying, how, as an IPCC author, do you keep hope alive? And this is actually something that we have to deal with first.
Yeah. I mean, I find this the sort of looking at this different scenarios really really important, because they are vastly different futures. And so think about the simulations I showed for New Zealand for end of century under about 2 degrees of warming versus under 4 degrees of warming or something. You go from complete devastation of the ice cover, it's pretty much all gone, to something that is still, it's not as, it's not today, but it's still recognizable. I think we have to accept that the climate is going to have, it's already having impacts which are significant, and we can't go back. But where we go from here has very different storylines depending on what emissions look like into the future. So the hope for me is convincing people that those sort of less bad effects are worth the investment.
Okay, so Alan's asking, is there a correlation with rainfall? How does rainfall affect glacier survival, that sort of thing?
Yep, so glaciers advance and retreat in response to a whole range of different climate drivers, but you can rank them, you can play around with models and look at the different sensitivities to changing drivers, and you can see that air temperature on a glacier like one you have in New Zealand is by far the most important driver of ice extent. And then precipitation is an important secondary driver, and there are others too. Wind speed, relative humidity, cloud cover. I mean, all of those things factor in. Yeah.
So Aidan is asking which areas should we be most concerned about? I guess maybe would we be most concerned about in Australia would be one way to address that.
Yeah.
And that are our current mitigation issue, procedures enough?
Yeah, so I don't think they're enough right now. I think we need to change. In fact, we're tracking not far off the worst case scenario. There's some good news. If you look at, this isn't my area, right? I work on the impacts on ice, but if you look at transitions in some countries, they're really far ahead of us. I'm always watching the renewable power generation in the United Kingdom, for example. There's nuclear there too, but they're burning less coal now than they have since the Industrial Revolution. Right? I think it's amazing.
Yeah, it's pretty cool. And I think South Australia is often exporting power.
Yeah. In Australia, the sort of impact of sea level rise it's going to depend a lot on where the ice melts, actually. So if you get more ice melt in Greenland, then it's bad for Australia. And if it melts more in Antarctica, it actually affects the Northern Hemisphere more. It's due to the complex geographic patterns of sea level rise that result from the impact of gravity and various other things on the sea level.
There you go. That's interesting. There's a good question here from Philip that I'm interested in knowing about too. Do we know yet when we're expecting the Arctic Ocean to be completely ice-free?
Yeah, it's not really my area. So that's a sea ice question. Land ice that I deal with is hundreds of meters to kilometers thick and sits on top of mountains, and sea ice is a few meters thick and covers the oceans. We have really terrific sea ice scientist in the school, Ariane Purik, who mostly works on Antarctic sea ice. But anyway, there are different projections for ice loss by mid-century and stuff like that, but I'm not really on top of which are most accurate.
There's another more of a geological question here from Justin Doe again. I'm going to ask the second half of the question. So one of the things that happens to continents as you take weight off the top is they actually tectonically lift up a little bit. That's called isostatic rebound for people who are listening. Do we know how much that contributes to sea level rise?
Yep. So what I was talking about before, actually, the fact that sea level rise is geographically different depending on where the ice melts. Answering that question of exactly what the sea level rise is going to be globally requires understanding of isostasy, which you just described, and also the gravitational effects. The isostatic effects from a changing ice load only extend over sort of hundreds of kilometers, or sort of at most. I mean, there are small effects that go further, but the major effects are sort of close by. So in Antarctica, as the ice sheet melts, the land will rise up, and the effects there are really strange, and they're kind of almost the opposite of what you might expect. And then the far field effects, like thousands of kilometers from the ice sheets, start to be influenced more by the gravitational controls. I mean, one of the things that I've got a colleague who works at the University of Massachusetts in the United States, and he's always talking about the irony of when Antarctica, especially when the West Antarctic ice sheet melts, the biggest impacts are going to be along the eastern seaboard of the United States, and he thinks that it's a historical justice playing out from burning fossil fuels over the last century.
That's a good one. Yeah, so Ego's asking some similar questions to what I was asking in terms of, you were talking mostly up to what's going to happen to 2100. He's kind of asking what's going to happen in the longer time frame, so beyond 2100 and maybe 1,000 years in the future.
So maybe the paleoclimate evidence gives the strongest constraints on that. So during the Pliocene, for example, when the Earth was about 3 degrees warmer, sea level was tens of meters higher than present. The best estimate's probably about 15 meters or so, but there's considerable uncertainty over that. But you can see that, you know, by the end of century, I would be shocked if we don't have 3 degrees of global warming. I mean, things really need to change to bring it in, you know, back to sort of 2 degrees. And a paleoclimate example there shows you that after a few thousand years, you'd expect, you know, roughly 15 meters of sea level rise. Now, I was showing you the impacts on Shanghai for, you know, a meter of sea level rise or something. Imagine what 15 meters would do to the world's coastlines. That's a
What is it if Antarctica's ice sheet completely goes?
It's about 60 meters. It's a lot, but there are sections of Antarctica that would be very, very hard to dislodge. And we can see that in climates that were much warmer than present, there was still significant ice there. You could lose about 20 meters of sea level equivalent from Antarctica under extreme warming. And then if you add 5 or 6 meters from Greenland and you know, 0.5 meter from all the world's mountain glaciers and some thermal expansion, you could get up to about 30 meters of sea level rise under the most extreme scenarios. I'm not trying to convince you that that's likely to happen anytime soon, but back in paleoclimate times, you know, you can find examples when sea level was 30 meters higher than present. It's preserved in you know, sedimentary records around the world's sedimentary basins. You know, we know it's happened before.
There's a slightly different question about ecosystem from Kathy here. How much flexibility is there in the Western Antarctic ecosystem? Is there potential for migration as the ice retreats, or is the ecosystem collapse more likely?
Yeah, look, I think the impacts of glacier and ice sheet retreat on ecosystems are really important, and I haven't talked about them at all tonight. It's actually an area that I've started to do a little bit of work on recently. It's a focus of SAFE, Securing Antarctica's Environmental Future, where there are really fabulous ecosystem scientists across the different Australian nodes, including Monash. My knowledge of this really is more around mountain glacier change and what it would do to ecosystems. In Antarctica, especially West Antarctica, most of the land is covered by ice, actually. And so the ecosystem impacts from a big retreat of the West Antarctic ice sheet would really play out on the continental shelf, where whole sections of shelf are suddenly exposed to light that have been covered by ice for thousands of years. And like the shallow marine sort of impacts would be profound. On land, the small areas that are ice-free could become more connected, and species that have been disconnected from each other for, you know, thousands or even millions of years would suddenly be in contact with each other, and we don't know how that's going to play out. I would guess, you know, mostly negatively in terms of you know, mixing things that really shouldn't be mixed together. So, you know, it's obviously, you can see I'm not an expert on this, but there's a very complicated sort of you know, system that might play out here and devastate biodiversity in certain areas where the ice disappears.
So there's a question here from Dave that might be a bit hard to answer, but I'll ask it anyway. He's asking, do you have a graph that shows glaciation, sea temperature, Earth core temperature, sea level, and sun temperature? So you probably have to choose your own adventure in how to answer that one. So we've got graphs of some of that stuff at the same time. So we would have, you know, graphs of glaciation and sea temperature and sea level and sun temperature over time, over the last, it's actually projected back quite a long way, isn't it? How far do the records go back now?
Records of
so paleoclimate.
Yeah, I mean, look, it depends a little bit. So ice core records, for example, go back nearly 1 million years. But there are other archives, you know, like, for example, the marine sedimentary record from ocean basins goes back millions of years, covers the whole centre. So, I mean, the history of the Earth during the period that the world's current oceans have opened is basically preserved in place. So for many decades now, like, there's been fabulous geological research led by IODP, the International Ocean Discovery Program, drilling holes and recovering paleoclimate records that tell us about past sea surface temperature, past ocean ice volume, all of these things collectively. And we know how the Earth's insulation from the orbital changes has occurred, and we have a bit of a record of solar changes through cosmogenic isotopes. So as the sun sort of heats up and cools down, it affects the Earth's magnetic field, which then changes the cosmogenic isotope flux into the Earth, and we get records of that preserved in archives. So we have a lot of that. Yeah.
I think from memory, the amount of sea level rise we might be getting to, or the temperature increase we might be getting to, is higher than we've seen for, I think, millions of years. The last several millions of years.
Yep. So like I was saying before, the mid Pliocene was sort of 2-3 degrees warmer than present, when there was roughly 15 meters of sea level rise. And to get back to 4 degrees or 5 degrees of global warming, I think you have to go right back into the earlier Cenozoic.
So how many millions of years is that for people? Quite a
15, I think, roughly. Yeah.
All right. So Alicia's got one. This might be the last one, actually. It might be fairly good timing, Alicia. Do you think the rise of sea level significantly impacts land use for food resource production?
Yeah, I think it does. I mean, the big deltas that I was talking about before are like bread baskets of the Earth.
Yep.
Yeah.
So the deltas are huge food baskets, and the deltas are the bits that are closest to the ocean,
and really close to sea. I mean, I lived in the Netherlands for a while, which was a lot of it is at sea level or slightly below sea level, and it grows a huge amount of Europe's food every summer. Yeah.
There's one that I didn't ask from Alan here about measurements of rainfall. So I didn't ask it straight away because I think rainfall is being recorded everywhere where there are glaciers, isn't it?
It's a bit of a gap, to be honest. So mountain meteorology is not as well understood as it should be, and one of the things we've tried to do over the years is install climate stations at high elevation, including rain gauges. But it's a bit tricky because a lot of the snow that falls is hard to capture in a rain gauge. You have to install special equipment. Yep. So yeah, it's definitely an area where more work needs to be done, and it does create uncertainty in projections of glaciers. But you can play around with the sort of upper and lower bounds on those uncertainties and still see you're going to get the same result.
All right. I think we've reached the end of the questions now. So I'd just like, on behalf of everybody who's been listening, I'd like to thank you very much for giving us a really interesting talk this evening, Andrew. I think I'll hand back.
Pleasure.
I think I'll hand back to Udi now.
Yes, thank you, Angie, and for moderating the session. Andrew, that was certainly a fascinating and an interesting talk. I'm sure there's still a couple of, I think there's one more question that's sort of come through, is it? Oh no, that's the last one. Yes, from Alan. That's fine. Yes, certainly there was lots of questions, and certainly sparked interest in all the audience members tonight. So for those who have joined us today, I will send in a feedback survey. So if you have any responses or if you have any questions afterwards, certainly send it through, and then I can forward it to Andrew for him to respond. Well, that brings us to the end of the session. Thank you, Andrew and Andy, for taking the time to present this webinar tonight, and also for all of you that have joined us and supported the webinar. So we will continue to do this series where we bring the different research from our 5 different schools, so that our alumni get to hear firsthand some of the work and the research work that we do in the Faculty of Science. Well, all the best. Thank you and have a great evening.